Hello everyone. Today we will study the central limit theorem. First of all, let me introduce what it is. Let S1, S2, and Sn be independent and identically distributed. Random variables. With means of mu and variance of sigma square. Let S bar then the random variable S bar be defined as then the random variable S bar be defined as S bar equal to S1 plus S2 plus Sn divided by n, which is average, which is the average of these random variables, the mean or the average of these random variables. The S bar be defined as S1 plus S2 plus Sn divided by n, which is the mean or the average of these random variables. Then, as n approaches to infinity, S bar tends to a normal distribution. With the mean of S bar equal to mu and the variance of S bar equal to sigma square over n. This is the central limit theorem. Let S1, S2, Sn be independent and identically distributed random variables with means of mu and variance of sigma square. Then the random variable S bar be defined as S bar equal to S1 plus S2 plus Sn over n, which is the mean of these random variables. Then as n approaches to infinity, S bar tends to a normal distribution with mean of especially value of S bar equal to mu and the variance of S bar equal to sigma square over n. So the central limit theorem says if there's a large amount of independent and identically distributed random variables, their average tends to a normal distribution. That's what the central limit theorem says. The actual proof for the central limit theorem is not easy, but here we do want to verify two things. Let's verify that especially value of S bar is mu and the variance of S bar is sigma square over n. Let's verify these two things. How do we verify that especially value of S bar equal to mu? Especially value of S bar is S1 plus S2 plus Sn over n. That can be rewritten as especially value of 1 over n times S1 plus 1 over n times S2 plus 1 over n times Sn. Then, for expected value of a linear combination of several random variables, I can separate the expected value. So I can write it as expected value of 1 over n times s1 plus expected value of 1 over n times s2 plus expected value of 1 over n times Sn. Then for expected values, I can pull out the coefficient of the variables, of the random variables. So I pull out 1 over n, I get 1 over n times expected value of S1 plus 1 over n times expected value of S2 plus 1 over n times expected value of Sn. And we know that these random variables, S1, S2, Sn, they are identical. If they are identical, they have exactly the same mean and variance. Their mean is u. So I get 1 over n times mu plus 1 over n times mu, because expected value of S1 is mu, expected value of S2 is mu, expected value of Sn is also mu. Here we have n terms. From S1, S2 to Sn, there are n terms. So if we have n terms, their sum is 1 over n times mu times n, since there are n terms. Then if we multiply, n get cancelled. We get mu here. So expected value of S bar is mu. Next, let's try to verify that variance of S bar is sigma squared over n. For variance of S bar, we first of all plug in S bar. S bar is S1 plus S2 plus Sn over n. Then this expression can be rewritten as variance of 1 over n times S1 plus 1 over n times S2 plus 1 over n times Sn. Since S1, S2, Sn, they are independent. Then I'm allowed to separate each random variables. So I can separate the random variables, write it as variance of 1 over n x S1 plus variance of 1 over n S2 plus variance of 1 over n Sn. Then I can pull out a coefficient. For variance, when I pull out a coefficient, I must square the coefficient. So I get 1 over n squared times variance of S1 plus 1 over n squared times variance of S2 plus 1 over n squared times variance of Sn. For variance, when I pull out a coefficient, I must square the coefficient. And then again, we know that S1, S2, Sn, they are identical random variables. Since S1, S2, Sn, they are identical, they must have exactly the same variance. Since they are identical, they must have exactly the same variance. And here we know that their variance is sigma squared. So I plug in sigma squared for variance of S1, S2, Sn. So I get 1 over n squared times sigma squared plus 1 over n squared times sigma squared. Every term looks exactly the same. 1 over n squared times sigma squared. And from S1, S2 to Sn, we know that there are exactly n terms. from S1, S2 to Sn, they are exactly n terms. Since every term looks exactly the same, I can take one of the terms times n. Since there are n terms, and every term looks exactly the same, so for their sum, I take one of the term multiplied by n. That's the sum of this sequence. Then 1 over n squared times sigma squared times n. If I cancel 1 over n here, I get sigma squared over n. So let's verify that variance of S bar is sigma squared over n. So that's the central limit theorem. Next, let me show you a corollary of the central limit theorem. A corollary is a simple theorem. Let the random variable y be defined as y equal to S1 plus S2 plus Sn. Then as n tend to infinity, y has a normal distribution, y tends to a normal distribution, with its special value of y equal to n times mu, and the variance of y equal to n times sigma squared. Let's prove it. Let's prove it based on the central limit theorem. We know that in central limit theorem, S bar S bar equal to S1 plus S2 plus Sn over n. Then if I multiply both sides by n, then n S bar equal to S1 plus S2 plus Sn equal to y. Then by central limit theorem, we know that as n tends to infinity, S bar tends to a normal distribution. Hence, y equal to n times S bar. Since S bar has a normal distribution, y equal to n times S bar also has a normal distribution. Next, let's verify the expected value and the variance. We know that expected value of y is expected value of n times S bar. Since y equal to S bar, y equal to n times S bar, expected value of y is expected value of n times S bar. Then for expected value, we are allowed to pull out coefficient. If I pull out n, I get n times expected value of S bar. And we know that expected value of S bar is mu. So expected value of y is n times mu. Next, let's verify variance of y. Variance of y is the variance of n times s bar. Then for variance, if I pull out a coefficient, I must square the coefficient. So if I pull out n, I must square n. I get n squared times variance of s bar. And we know that variance of s bar is sigma squared over n. Here I cancel one of the n. I get n times sigma squared. So if y is the sum of the independent identically distributed random variables, then y also, as n tends to infinity, y also tends to a normal distribution, where its special value of y is n times mu, and variance of y is n times sigma squared, which is the variance of x. In addition, one of the conditions of the central limit theorem says n approaches to infinity. That means, in order to have a good approximation using central limit theorem, n must be large enough. N must be large enough. But how large means large enough? In general, in order to have a good approximation using the central limit theorem, n must be 30 or greater. N must be 30 or more. So note, keep this idea in mind. In order to have a good approximation, using the central limit theorem, the sample size n must be large enough. In general, n must be 30 or greater. N must be 30 or greater. If n is less than 30, we can still using central limit theorem. We can still use the central limit theorem, but approximation, the answer is not very accurate. If n is less than 30, we can still use the central limit theorem, but the answer is not very accurate. Next, let's look at an example. When 100 numbers are randomly chosen from the interval 0 and 10, find each of the following probabilities. Part A, what's the probability that the average of these 100 numbers is between 5.25 and 5.75? Part B, what's the probability that the sum of these 100 numbers is more than 470? Let's set out the problem first. When numbers are chosen from the interval from 0 to 10, that means every number in the interval have the same chance to be chosen. That's a continuous uniform distribution. That's a continuous uniform distribution. So let's set out a problem first. Let the random variable x represent the value of the total number Let the random variable x represent the value of the total number from the interval. Then x has a continuous uniform distribution. From the interval from 0 to 10. Then in the earlier section, we know that if x has a uniform distribution from alpha to beta, its special value of x is alpha plus beta over 2, and variance of x is beta minus alpha squared over 12. That's what we learned in the earlier section. Here, since x has a continuous uniform distribution, its special value of x is alpha plus beta over 2. That's alpha, that's beta. We have 0 plus 10 over 2. Which is 5. And the variance of x is beta minus alpha squared over 12. Here, that's alpha, that's beta. If I plug in, I get 10 minus 0 squared over 12, which is 100 over 12. That's the variance of x. And that's how we set out a problem. Now answer the question. Part A. What's the probability that the average of these 100 numbers is between 5.25 and 5.75? Here we let x bar be the average. Let x bar be the average of these 100 numbers. Then, by central limit theorem, we know that x bar has a approximately normal distribution. Its special value of x bar is the same as its special value of x. Its special value of x bar is the same as its special value of x, which is 5. And the variance of x bar is the variance of x over n. Variance of x bar is variance of x over n. By central limit theorem, variance of x bar is the variance over n. Sigma squared is variance. That's variance of x over n. Mu is its special value of x. Its special value of x bar is its special value of x. Variance of x bar is variance of x over n. And then we know that variance of x is 100 over 12 divided by n. N is the sample size. Here we are choosing 100 number from the interval, so the sample size is 100. Here we're choosing 100 numbers out of the interval, so the sample size is 100. N is 100 here. 100 over 12 divided by 100 is 1 over 12. So we know that mu of S bar is 5. Mu of S bar is special value of S bar, that's 5. Sigma of S bar is square root of the variance. That's square root of 1 over 12. Sigma of S bar is the square root of the variance of S bar. That's 1 over 12. Now answer the question. What's the probability that the average of these 100 numbers is between 5.25 and 5.75? We're looking for the probability that S bar is between 5.25 and 5.75. According to central limit theorem, when n is large enough, S bar has approximately normal distribution. Since x has a normal distribution, we can convert x to the standard normal distribution, and then find the probability using the standard normal CDF, using the table of the standard normal CDF. So here, let's convert x bar to z, to the standard normal distribution. The conversion for z is z equal to x minus mu over sigma. And same thing works for S bar. Here we use S bar minus mu over sigma. Here we use S bar minus mu over sigma. So we have 5.25 minus mu. Mu is 5 over sigma. Sigma is radical 1 over 12. Same thing. For 5.75, we use 5.75 minus mu. Mu is 5 over sigma. Sigma is radical 1 over 12. Then use calculator. (5.25) minus 5 over radical 1 over 12 I use my calculator, round to 2 decimal places. I get probability of 0.87. And for this number, 5.75 minus 5 over radical 1 over 12. I use my calculator, round to 2 decimal places. I get 2.60. In order to find a probability using the table of the standard normal CDF, I must rerun the probability, put it in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of z. They both equal to phi of z. So this probability here can be rewritten as probability that z is less than 2.60 minus probability that z is less or equal to 0.87. That's phi of 2.60 and that's phi of 0.87. Then use the table of the standard normal CDF, find the probabilities. That's the table of the standard normal CDF. First of all, let's find phi of 2.60. Phi of 2.60 is here. 0.99534. 0.99534. Next, we need to find phi of 0.87. Phi of 0.87. 0.87 is here. It's 0.80785. 0.80785. Then subtract the numbers. I subtract this number using my calculator. I get 0.18749. In general, we run the answer to 4 decimal places. That's approximately 0.1875. That's the probability that the average of this 100 number is between 5.25 and 5.75. When the sample size n is larger than 30, that's a very good approximation. Now, part B. What's the probability that the sum of these 100 numbers is more than 470? What's the probability that the sum of these 100 numbers is more than 470? So for part B, let y be the sum of these 100 numbers. Let y equal to S1 plus S2 plus S100. Let y be the sum of these 100 numbers. Then by central limit theorem, we know that y has approximately normal distribution. Its special value of y. Its special value of y is n times its special value of x. Its special value of y is n times its special value of x. Here n is 100, the sample size is 100. Times its special value of x. Its special value of x is 5. So we get 100 times 5, that's 500. That's its special value of y. Next, let's find variance of y. Variance of y is n times variance of x. By central limit theorem, variance of y is n times variance of x. Its special value of y is n times its special value of x. Variance of y is n times variance of x. Here mu is its special value of x. Sigma square is variance of x. So its special value of y is n times its special value of x. Variance of y is n times variance of x. Here n is 100. Variance of x is 100 over 12. Variance of x is 100 over 12. Then multiply, we get 10,000 over 12. That's its special value of y and the variance of y. Next, we can find mu of y and sigma of y. Mu of y is the same as its special value of y which is 500. Sigma of y is the square root of the variance of y. Sigma of y is the square root of the variance of y. That's square root of 10,000 over 12. That's the variance of y. Now answer the question. What's the probability that the sum of these 100 numbers is more than 470? We're looking for the probability that the sum of these 100 numbers is more than 470. By central limit theorem, we know that y has an approximately normal distribution. Since y has a normal distribution, we can convert y to the standard normal distribution, and then use the table of the standard CDF, standard normal CDF, to find the probabilities. First of all, convert y to the standard normal distribution. Convert y to z, the standard normal distribution. The formula is very similar. Z equal to y minus mu over sigma. Z equal to y minus mu over sigma. 470 minus mu of y is 500 over sigma of y. This radical 10,000 over 12. Then use calculator. That's the probability that z is greater than this number. Use calculator, round to 2 decimal places. Here I get negative 1.04. Here I get negative 1.04. Next, in order to use the table of the standard normal CDF, I must run the probability in the form of z less or equal to some number, or z less than some number. They both equal to phi of z. So here I can use the complement. If I use the complement, probability that z greater than negative 1.04 is the same as 1 minus probability that z less or equal to negative 1.04. That's phi of negative 1.04. Then use the table, find phi of negative 1.04. Negative 1.04 is here. I get 0.14917. I get 0.14917. I get 0.14917. Then use calculator. 1 minus 0.14917 is 0.85083. In general, we want to answer to 4 decimal places. That's 0.8508. That's the probability that the sum of these 100 numbers is more than 470. Next example. In a bag, there are 4 red marbles, 2 blue marbles, and 3 green marbles. Consider an experiment of choosing 6 marbles from the bag without replacement. When this experiment is repeated 200 times, what's the probability that the total number of obtained green marbles is more than 415? So let's set down a problem first. Since we are choosing marble from the bag without replacement, and we are looking for green marbles, we can consider success is green marble, so there are 3 success. The failures are non-green marbles, so the failures is 4 plus 2, there are 6 failures. And we are choosing 6 marbles from the bag. Here we can consider hypergeometric distribution. Since we are choosing marble without replacement, we can consider hypergeometric distribution. So let x, then the random variable x represent the number of obtained green marbles. In the experiment. Here we consider green marble as success. Non-green marbles are failures. We are choosing 6 marbles without replacement. Here we can consider X has a hypergeometric distribution. X here has a hypergeometric distribution. Then n equal to 6. We are choosing 6 marbles. N1 is 3. There are 3 success. N2 is 6. There are 6 failures. 4 red marble plus 2 blue marble. There are 6 failures. Then, in the earlier section, we know that for hypergeometric distribution, its special value is n times n1 over n1 plus n2. Variance of x is n times n1 over n2 plus n1 plus n2 times n2 over n1 plus n2 times n1 plus n2 minus n over n1 plus n2 minus 1. So let's find a special value and variance first. A special value of x is n times n1 over n1 plus n2. Here n is 6, n1 is 3, n1 plus n2 is 9. 3 over 9 is 1/3. 6 times 1/3 is 2. So its special value of x is 2. Next, let's compute variance of x. Variance of x is n times n1 over n1 plus n2 times n2 over n1 plus n2 times n1 plus n2 minus n over n1 plus n2 minus 1. N times n1 over n1 plus n2 times n2 over n1 plus n2 times n1 plus n2 minus n over n1 plus n2 minus 1. Then plotting numbers. Here n is 6, n1 is 3, n1 plus n2 is 9, n2 is 6, n1 plus n2 is 9 times n1 plus n2 minus n. n1 plus n2 is 9 minus n is 6. 3 plus 6 minus 6 is 3. The denominator n1 plus n2 minus 1. n1 plus n2 is 9. 9 minus 1 is 8. Then simplify. Calculate this. Here I use my calculator. I get half. Here I use my calculator. I get half. So variance of x is half. Let's now set up to this problem. Next, let's answer the question. When this experiment is repeated 200 times, what's the probability that the total number of obtained green marbles is more than 415? Here, x represents the number of obtained green marbles in one experiment. And we are looking for the total number of obtained green marbles in 200 experiments. So let y equal to S1 plus S2 plus x200. S1 represents number of obtained green marble in the first experiment. S2 represents number of obtained green marble in the second experiment. S200 represents number of obtained green marble in the last experiment. Altogether, y is the total number of obtained green marbles in all 200 experiments. Then, since y equal to S1 plus S2 plus S200, by central limit theorem, its special value of y is n times its special value of x. Here, n is 200, since we repeat the experiment 200 times. N is 200. Its special value of x is 2. Its special value of x is 2. 200 times 2 is 400. That's its special value of y. Next, let's try to find variance of y. Variance of y is n times variance of x. variance of y is n times variance of x. Here n is 200. Variance of x is half. 200 times half is 100. So mu of y is expected value of y, which is 400. Sigma of y is square root of the variance of y, which is square root of 100. Square root of 100 is 10. So that's mu of y, and that's sigma of y. Next, let's answer the question. We are looking for the probability that the total number of obtained green marbles is more than 415. We're looking for the probability that y is more than 415. Since y is the sum of 200 independent, identical distributed random variables, according to central limit theorem, y has an approximately normal distribution. Y has an approximate normal distribution. Since y has an approximate normal distribution, I can convert y to the standard normal distribution, then use the table of the standard normal CDF to find the probabilities. Let's first of all convert y to the standard normal distribution. Convert y to z first. The formula to convert x to z is z equal to s minus mu over sigma. So the same thing works for y. Take y minus mu of y. Mu of y is 400 over sigma of y. Sigma of y is 10. In general, the formula is z equal to s minus mu over sigma. Here we can also apply y. I get y minus mu of y over sigma of y. Then use calculator. Round the answer to 2 decimal places. 415 minus 400 over 10. Round the answer to 2 decimal places. I get 1.50. So that's the probability that z is greater than 1.50. Next, in order to use the table of the standard normal CDF to find the probabilities, I must derive a probability in the form of z less or equal to some number, or probability that z is less than some number. That's phi of the number. They both equal to phi of the number. So here we have probability that z is greater than 1.50. I can use the complement. That's 1 minus probability that z is less or equal to 1.50. That's 1 minus phi of 1.50. Then I can use the table of the standard normal CDF to find the probabilities. That's a table of the standard normal CDF. We're looking for phi of 1.50. 1.5 is here. 1.50 is here. 0.93319. 0.93319. I get 1 minus 0.93319. Then 1 minus 0.93319 is 0.06681. In general, we round the answer to 4 decimal places. So that's 0.0668. It's approximately 0.0668. That's the probability that the total number of obtained green marbles is more than 415. Next example, the average burning time of a certain type of lamp is 20 hours. Suppose there are 300 such lamps. What's the probability that the average burning time of the lamps is less than 21 hours? Let's set out the problem first. We know that the average burning time of a certain type of lamp is 20 hours. If we know the average waiting time for the occurrence of an event, we can use exponential distribution. So let's set out the problem first. Let x represent the burning time of a lamp of this type. Since we know the average waiting time of the occurrence of an event, we can use exponential distribution. Then X has an exponential distribution with theta equal to 20, because the average waiting time for the occurrence of an event is 20 hours. The average burning time of this type of lamp is 20 hours. That's an average waiting time for the occurrence of an event. And next, in the earlier section, we know that if X has an exponential distribution, its special value of X is theta. Variance of X is theta squared. Its special value of X is theta. Variance of X is theta squared. Then we know that its special value of X is theta, which is 20. Variance of X is theta squared, which is 20 squared, equal to 400. That's its special value of X, and that's variance of X. So that's the setup to the problem. Next, let's answer the question. Suppose there are 300 such lamps. What's the probability that the average burning time of the lamps is less than 21 hours? So let X bar represent the average burning time of this type of lamps. By central limit theorem, we know that S bar has a normal distribution. Its special value of S bar is the same as its special value of X. Its special value of S bar is the same as its special value of X. And its special value of X is 20. Variance of S bar is variance of X over N. Variance of S bar is variance of X over N. Variance of X is 400. N is the sample size. We have 300 this type of lamps. So N is 300. 400 divided by 300 is 4 over 3. That's the variance of S bar. Next, we are looking for the probability that the average burning time of the lamps is less than 21 hours. So we are looking for S bar, the average waiting time, is less than 21. According to central limit theorem, we know that S bar has approximately normal distribution. S bar has an approximate normal distribution. So I can convert S bar to the standard normal distribution. Then use the table of the standard normal CDF to find the probabilities. Let's first of all convert S to Z. The formula for conversion in general is Z equal to S minus mu over sigma. And it also works for S bar. It also works for S bar. Here, mu of S bar is 20. Sigma of S bar is the square root of the variance of S bar. Sigma of S bar is the square root of the variance, which is square root of 4 over 3. Sigma of S bar is the square root of the variance, which is square root of 4 over 3. Then use the formula. Z equal to S minus mu over sigma. So we have 21 minus mu over sigma. Then use calculator. Round to 2 decimal places. Use calculator, round the answer to 2 decimal places. Here I get 0.87. Here I get 0.87. Probability that Z less than 0.87. That's phi of 0.87. That's phi of 0.87. Next, I can use the table. That's the table of the standard normal CDF. 0.87 is here. 0.87, that's 0.80785. 0.80785. 0.80785. Then in general, we run the answer to 4 decimal place. Answer is 0.8079. That's the probability that the average burning time of these 300 lamps is less than 21 hours. Next example, let the random variables S bar and Y represent the mean and the sum of a random sample of size 15 from the distribution whose PDF is f of x equal to 3 over a s squared if s is between 0 and 2 and 0 otherwise. Find the probability that absolute value of s bar minus 1.5 is less than 0.2 and the probability that y is between 22 and 25. Let's set down a problem first. Here, S bar and Y represent the mean and the sum of a random sample of size 15 from the distribution, whose PDF is f of x. So let's first of all find its expected value and the variance first. So let the random variable x represent random variable x be the probability distribution whose PDF is f of x. Next, let's compute its mean and variance. Its special value of x is the integral from negative infinity to infinity, x times f of x dx. Here the support is from 0 to 2. So take integral from 0 to 2, since the support of x is from 0 to 2. Since support of x is from 0 to 2, take integral from 0 to 2. X times f of x in the support. F of x in the support is 3 over a times s squared dx. Let's multiply x. I get 3 over a s cubed dx. Next, take antiderivative with respect to x. I get 3 over a times x raised to power 4 over 4. Evaluate from 0 to 2. If I plug in 2 for x, 2 raised to power 4 is 16. 16 divided by a is 2. 2 over 4 is 1 over 2. So I get 3 over 2. If I plug in 0 for s, I get 0. So the answer is 3 over 2 minus 0 is 3 over 2. That's the expected value of x. Next, we try to compute the variance of x. We know that variance of x is always expected value of x squared minus expected value of x squared. That's the variance of x. In order to find a variance, let's compute expected value of x squared first. Expected value of x squared is the integral. Since x is continuous random variable, we take integral from negative infinity to infinity. Take s squared times f of x dx. We know that support of x is from 0 to 2. So take integral from 0 to 2. S squared times f of x. F of x in the support is 3 over a times s squared dx. Then we multiply s squared to s squared. If I multiply s squared to s squared, I get x raised to power 4. So let's integral from 0 to 2. 3 over a times x to the power 4 dx. Next, take antiderivative with respect to x. I get 3 over a times x raised to power 5 over 5. Evaluate from 0 to 2. If I plug in 2 for x, 2 raised to power 5 is 32. 32 over a. 32 divided by a is 4. 3 times 4 is 12. I get 12 over 5. If I plug in 0, I get 0. So the answer is 12 over 5 minus 0 is 12 over 5. That's a special value of x squared. Next, we can find the variance. Variance of x is a special value of x squared minus a special value of x squared, which is 12 over 5 minus a special value of x is 3 over 2. 12 over 5 minus 3 over 2 squared. That's 12 over 5 minus 9 over 4. Cross multiply, that's 48 minus 45. That's 3 over 5 times 4 is 20. So variance of x is 3 over 20. A special value of x is 3 over 2. Variance of x is 3 over 20. So a special value of x is 3 over 2. Variance of x is 3 over 20. Let's then set up to the problem. Now next, let's answer the question. Let's find the first property here. Find the probability that S bar minus 1.5 is less than 0.2. Here S bar represents the mean of the sample. Find the probability that S bar, absolute value of S bar minus 1.5 is less than 0.2. Let's first of all compute a special value of S bar. By central limit theorem, we know that a special value of S bar is the same as a special value of x, which is 3 over 2. And variance of S bar is variance of x over n. Variance of S bar is variance of x divided by n, where n is the sample size. We know that variance of x is 3 over 20 over n. N is the sample size. Here the sample size is 15. Then we have 3 over 20 times 1 over 15. Divide top and bottom by 5. I get 1 over 100. That's variance of S bar. So mu of S bar. Mu of S bar is the same as the special value of S bar, which is 3 over 2. Sigma of S bar, that's the square root of the variance of S bar. That's square root of 1 over 100. Square root of 1 over 100 is 1 over 10. And we are looking for probability that absolute value of S bar minus 1.5 is less than 0.2. Let's rewrite the probability first. Absolute value of S bar minus 1.5 is less than 0.2. That means S bar minus 1.5 is between negative 0.2 and positive 0.2. If I add 1.5 to all three of them, I have probability that S bar is between 1.3 and 1.7. According to central limit theorem, we know that S bar has an approximate normal distribution, so I can convert X bar to the standard normal distribution. The formula for conversion is in general, is Z equal to S minus mu over sigma. Same thing works for S bar. So I take 1.3 minus mu of S bar, that's 3 over 2. Divided by sigma of S bar, that's 1 over 10. Then on the other side, take 1.7 minus mu of S bar over sigma of S bar, which is 1 over 10. Then use calculator. round the answer to 2 decimal place. Use calculator. Round the answer to two decimal place. Here I get negative 2.00. On the other side, I get positive 2.00. That's the probability that z is between negative 2.00 and positive 2.00. In order to find a probability using the table of the standard normal CDF, we must rewrite the probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of z. They both equal to phi of z, phi of the number. They both equal to phi of this z, phi of the number. So here, I can rewrite this probability as probability that z is less than 2.00 minus probability that z is less than less or equal to negative 2.00. That's phi of 2.00 minus phi of negative 2.00. Then I can use the table of the standard normal CDF to find the probabilities. That's the table of the standard normal CDF. Phi of 2.00 is here. It's 0.97725. 0.97725. 0.97725 minus phi of negative 2.00. Negative 2.00 is here. Negative 2.00 is here. It's 0.02275. 0.02275. Then subtract. I get 0.9545. That's the probability that absolute value of S bar minus 1.5 is less than 0.2. Now let's answer the other question. What's the probability that y is between 22 and 25? What's the probability that y is between 22 and 25? Here, y represents the sum of this random sample. Y represents the sum of this random sample. So, y represents the sum of S1, S2, and S15. According to central limit theorem, its special value of y is n times its special value of x. Its special value of y is n times the special value of x. Here, n is 15, since there are 15 samples. Its special value of x is 3 over 2. 15 times 3 over 2 is 45 over 2. That's its special value of y. Next, for the variance of y, according to central limit theorem, that's n times variance of x. N is the sample size, which is 15. Variance of x is 3 over 20. Here I can divide top and bottom by 5. I get 9 over 4. That's the variance of y. So, mu of y is the same as its special value of y. That's 45 over 2. Sigma of y, that's the square root of the variance of y. That's square root of 9 over 4, which is 3 over 2. That's the variance of y. We are looking for a probability that y is between 22 and 25. Y is between 22 and 25. According to central limit theorem, y is the sum of 15 independent identically distributed random variables. Y also has an approximately normal distribution. Y also has an approximate normal distribution. So I can convert y to the standard normal distribution. Then use the table of the standard normal CDF to find the probabilities. Let's first of all convert y to z, the standard normal probability, standard normal distribution. Let's first of all convert y to z. the standard normal distribution. The formula for conversion in general is z equal to s minus mu over sigma. The same thing works for y. So I can take 22 minus mu of y over sigma of y. Then take 25 minus mu of y over sigma of y. Then use calculator, round the answer to 2 decimal places. Use calculator, round the answer to two decimal places. Here I get negative 0.33. The other side is positive 1.67. In order to find the probability using the table of the standard normal CDF, we must rerun the probability in the form of probability that z less than some number, or probability that z less than some number. Either z less or equal to some number, or z less than some number. They both equal to 5 of the constant here. So this probability can be rewritten as probability that z is less than 1.67 minus probability that z is less or equal to negative 0.33. That's 5 of 1.67, and that's 5 of negative 0.33. Then use the table of the standard normal CDF to find the probability. 1.67 is here. It's 0.95254. 0.95254. Next, find 5 of negative 0.33. 0.3 is here. 0.33 is here. That's 0.37070. 0.37070. Then subtract. I get 0.5814. In general, for the final answer, round to 4 decimal places. Here I get 0.5818. So the probability that the sum of these 15 numbers is between 22 and 25 is 0.5818. Note, for this example, the sample size is only 15. The sample size is only 15. So that's not a good approximation. This answer is not very accurate. In general, in order to use the central limit theorem, the sample size must be at least 30. If the sample size is below 30, we can still use it. We can still use the central limit theorem, but the answer is not very accurate. The answer is not very accurate. In this example, since the sample size is less than 30, this answer here is not very accurate.